Okay, so today's lesson is going to be on the number system. Um, if you don't have this paper, you can go ahead and copy it down on a regular sheet of paper, and we're going to be filling this out as we go along. Alternatively, the other option is for you to click print on the PDF that's attached to Google Classroom, or wait until you get a paper from me, and then that way you have the worksheet in front of you, and then you can go ahead and put it on your folder for the fill-in notes. Okay, so let's go ahead and start talking about what numbers are. Up until this point, you've probably dealt with numbers that are real. Okay, every single number that you've worked up as in middle school and elementary school have been real numbers. But those numbers have been other types of numbers as well, which we are going to go ahead and start defining these, so that way you can kind of see what each number falls into. So we're actually going to go ahead and see. Let's see. It says any number that we have been using so far is a real number. Real numbers are numbers that include both rational and irrational numbers. And we're going to define what that is in a little bit. Okay. So let's go ahead and start with the first one, a natural number. A natural number is like the numbers that you learned when you were really, really, really small, right? So what do you teach a baby? Like, what's the first number they learn? It's probably the number one. So natural numbers are basically going to be those basic numbers, which you start with one and go to two, three, four, five, and so on. These are essentially counting numbers. So all of the counting numbers are natural numbers. So that takes care of what a natural number is. It's basically any number that you would count. Now, you can count pretty high, okay? So just because I didn't write them down, I want you to understand like you can count up to 105. That's still a natural number because you would count up to that number, okay? Once you got a little bit older, though, maybe around the age of 4 or 5, someone introduced to you the idea of zero, right? You don't start with the number zero, but it is one of the numbers that you learn fairly early in your life. So a whole number is going to be all the natural numbers, including zero. So the smallest whole number we can get is zero, and then followed by one, two, three, four, and so on and so forth. So we say that a whole number is zero and all the natural numbers or the counting numbers. Now, what I want you to notice right here is that every single number that's a natural number, so if, for example, 3 is also a whole number. So 3 is a natural number and is a whole number. Any number that you pick from this list is in this list. So if I pick 8, is a natural number, it also happens to be a whole number. That doesn't go the other way because, like, let's say 0 is a whole number, but 0 is not a natural number. So it doesn't go the other way. Any number that's a natural number is automatically a whole number, but it doesn't work in the other direction. Okay. All right. So we got the natural numbers, which are their counting numbers, and then we have the whole numbers, which are all the natural numbers as well as the number 0. Now we're going to go ahead and try to figure out, well, what is an integer? An integer is basically all of the whole numbers and its opposite. Now, when I say opposite, like the opposite of 4 is -4. The opposite of 7 is -7. To make it a little bit more difficult, the opposite of -9 is +9. And then to make it even harder, the opposite of 0 is 0. So integers are going to be all of those natural numbers along with its opposites. So I can't start at the beginning because there's too many, but I'm going to go ahead and start here at -4, -3, -2, -1, 0, 1, 2, 3, and 4. These are all integers. Now, again, this doesn't stop here, so we're going to keep on going. And the same thing in the beginning, it does not stop there. It actually started way before that. So, as far as what integers are, remember we said that integers are all the whole numbers and the opposites. All the whole numbers and their opposite. Just like before, anything that is a whole number is automatically an integer. So for example, the number 4 is a natural number, and since it's natural, it's a whole number, and since it's a whole number, it's an integer. So we can go up, we just can't go down on the list because a negative 4 is not a whole number. It's an integer, but it's not a whole number, so it goes one direction only. Okay, so those are the easy numbers to categorize. The harder ones are the ones that begin here when we start talking about what a rational number is. So a rational number is a number that can be written as a fraction. I'm going to write this right here. In fact, you know what? I forgot to write these. Can you do me a favor? And on your notes, can you go ahead and put all of these definitions in thought bubbles? That way we can kind of separate them, and I know what the actual definition is of each one. Okay. So now we said we're talking about a rational number. A rational number is, it's going to be a weird definition, okay? A rational number is going to be a number that can be written as a fraction. A over B, where B cannot be 0. And the reason B cannot be 0 is because if B is on the denominator, then you're going to try to divide by 0. If you try to divide by 0 on your calculator, it's going to say domain error or undefined or something to that extent. Okay, it's going to say, I think it's domain error if I remember correctly. Okay, let's give you some examples of rational numbers. We're going to start easy and then we're going to make it more difficult as we go along. Okay, so an easy example of this would be like the number 2/3. 2/3 is a rational number because I can write it as a fraction. Okay, 2 over 3. Okay, so that's an easy one. If I wanted to make it a little bit more complicated, I can do something like this. Negative 4 over 3. That is a rational number because I can write it as a fraction using integers, okay? All right, let's get a little bit more creative. What about the number 5? 5 is a rational number. Now remember, I said I have to write it as a fraction, right? It is a rational number because 5 is the same thing as 5 over 1. They're exactly the same. Therefore, since 5 is the same thing as 5 over 1, and 5 over 1 is a fraction, then 5 is rational, okay? So all of these numbers right here, I can change into fractions by putting a 1 on the bottom, which means all these integers are also rational numbers, okay? But just like before, 2/3 is a rational number, but it is not an integer. So it doesn't go both ways. All right, what else can I do that's kind of complicated? Well, I can do something like this. What about the square root of 49? I know that the square root of 49 is 7, and I know that 7 is the same thing as 7 over 1. So square root of 49 is the exact same thing as 7. It's the exact same thing as 7 over 1, and 7 over 1 is a fraction, which means the square root of 49 must be rational. Okay. There are more examples. However, we're going to skip those other examples for now. We're actually going to skip our way down to the bottom. And on your worksheet, you should have some fill in the blanks. I'm not sure if they're exactly like this, but we're going to do our best with this, okay? For this part of the notes, I need you to have highlighters. So make sure you have like 3 or 4 different colored highlighters on you because we are going to be using them right now. So let's see, fill in the blanks. Here we go. Rational numbers are numbers that can be written in the form P over Q, where P and Q are integers and Q is not equal to 0. It's the exact same definition that I gave you above. The only difference is instead of P and Q, I'm using A and B, but they are the exact same thing. Basically, they're saying if it's a rational number, then it can be written as a fraction. What I want you to do is I want you to take any color highlighter that you want. I'm going to go ahead and pick blue. I want you to highlight my vocabulary word, which in this case is rational numbers. And the important thing about rational numbers is they can be written in the form P over Q, where P and Q are both integers, and Q is not equal to 0. You cannot have the bottom number be 0 because, again, you end up with something that's not a number, right? It just says error or domain error. All right, let's give you some other vocabulary. A terminating decimal. What's a terminating decimal? A terminating decimal is a decimal that ends, that means it has no remainders, or it terminates. So let's go ahead and write or highlight with a different colored highlighter. I'm going to write that a terminating decimal is going to be a decimal that ends or terminates. That means the decimal stops. For example, 4.192. 4.192, I stopped talking, right? Like 192, and that is where it ends. If you have a terminating decimal like that, then there is a trick to changing that into fractions. We're not going to go over the trick, but understand if it ends, you can change it into a fraction. If you can change it into a fraction, then that means a terminating decimal is a rational number. So what is that telling me? That means if I have something like this, 4.192, because it terminated, because the decimal ended, then it's automatically a rational number. It's a nice decimal. Very clean. Or the next definition that we have is a repeating decimal. Go ahead and take a different colored highlighter, and we're going to go ahead and highlight that vocabulary word. A repeating decimal is a decimal in which one or more of the digits repeat infinitely. So I want you to highlight that it's a decimal where the digits repeat infinitely. What does that look like? Well, that's going to look something like this. 3.777777777 with the line on top. If it goes on forever, which this one does, okay, but the decimal repeats itself, there is a trick into changing that into a fraction as well. And if you can change it into a fraction, then it's a rational number. Again, we're not going to go over the trick today. We might go over it down the line, but for right now, you just need to know if it's a decimal that goes on forever, but it repeats, then you can change it into a fraction, which means it's rational. Okay. In fact, even if it looks like this, like 3.164, and then all of a sudden it goes 4, as long as it goes on forever and it repeats, you can change that into a fraction, which means it's a rational number. So let's say you have a whole number. Since it's a whole number, it's an integer. Since it's an integer, it's a rational number. And since it's a rational number, it's a real number. However, this 3.16444444444, it's a real number because it's rational, but that is not an integer. That doesn't work out going the other way. Okay? All right. So basically, what I'm trying to tell you is just because it's a decimal does not mean it's automatically irrational. Okay? It can be rational as long as the decimal stops, or if the decimal repeats infinitely, then it can be a rational number. However, the next definition says irrational numbers are numbers that cannot be written in the form P over Q. So you can go ahead and start using those same colors again because I know you might be running out. Irrational numbers are numbers that cannot be written in the form P over Q. How do we know it can't be written in the form P over Q? Well, because of two things. Number one, it's non-terminating, and it's non-repeating. That means you're talking about decimals that never end and never repeat. So if they don't end, if you have a decimal that does not end and it doesn't repeat, then that's when you're going to end up with an irrational number. Let's go over some of those examples. What do those examples look like? Well, one of them looks like this. The most famous example of an irrational number would be pi. If you remember from middle school, pi is a number, and I think most of you guys remember it as 3.14, but technically that's close. That's not perfect. If I wanted the full number of pi, I would go like 3.14159.2, and I think it's like 625, but I don't remember. But it keeps going. What do I want you to notice about this decimal? This decimal, does it stop like this one? Nope. It keeps on going. So unfortunately, that didn't work. Okay, well, I know it keeps on going, but does it repeat? Nope, because I don't see a pattern here. Like, I don't know what the next number is going to be, right? So it's not something that repeats forever. So in this case, it doesn't stop and it doesn't repeat, then it's irrational. All right, what's some other examples? Well, let's see. If I have a number like this, 14.1938617. Got a question for you. We're going to keep going. Do you know what the next number is going to be? Nope. So then it's not repeating. And then did it stop? Nope. So then again, you're dealing with an irrational number. Okay, let's give you one more example. What about the square root of, let's go with square root of 15. That one's a little bit harder, right? Because look, I got something that looks like that. Square root of 49 I know is 7, and the 7 is the same thing as 7 over 1. Therefore, it's rational. What about the square root of 15? Well, the square root of 15, if I were to type that in my calculator, I would end up with a number like 3.8, whoops, 3.872983, and that's as far as my calculator goes. Hey, that's all the numbers I see on my calculator. Now, at this point, it's really important for you to think, is it that my calculator finished, or is it that my calculator had so many numbers on the screen that it just gave up? In this case, it had so many numbers on the screen that it just gave up. So it's not that this number stopped. It did not. It's just your calculator doesn't have enough space to fill in the rest of the numbers. It gave up. Okay. So now I know this goes on forever. It does not terminate like this one did. And it definitely doesn't repeat like these ones did. So it did not terminate and it did not repeat. Therefore, it is irrational. And just know that if it's irrational, it's still a real number. Okay. Okay. That's all the examples we have for today. If you have any questions, feel free to email me and make sure that you put this eventually in your notebook.